Welcome to today's lesson, which is lesson number 20 of the course on industrial automation and control. Today, we are going to look at some new programming elements, namely timers, counters, etc., which are required for RLL programming. We are going to understand their meanings and see their use in real simple, but real typical industrial programs. So, before we get on, we take a look at the instructional objective, which is so that a student will be familiarized, or he will be able to describe various types of timers used in relay ladder logic. He will be able to describe a counter. He will be able to construct RLL programs for simple problems involving these timers and counters, and he will also be able to be familiar with some program control, data transfer and arithmetic instructions, which are required in, just like in any program you require if then else statements, which are program control statements, add statements, you need statements for moving data from one location to the other. So, here also you need such constructs. So, for writing complete programs, they are sometimes necessary. So, we will get familiarized with some of them. Of course, we must remember in this context that there are relay ladder logic programs are often somewhat non-standard. So, it is not that we are following a particular manufacturer's constructs, but it is very likely that most of these constructs will be found in each PLC manufacturer's programming repertoire. So, it is good to understand them in an abstract form, and then if you are going to use a particular PLC, then look up the particular manual for such constructs. So, before we use timers and counters, we want to motivate them. So, we take a second look at our previous example of the die press. So, here is the die press, where basically there is the piston moves the die up or down depending on whether the up solenoid or the down solenoid is activated. This directs hydraulic power upward or downward to the piston. So, the die moves up or down, and there are two sensors, namely the upper limit switch and the lower limit switch, which sends the positions of the end positions of the die. So, we take a look at the earlier solution which we proposed before in an earlier lesson. So, here what we did is here we proposed an RLL program which used only the normally on and the NO, and there is a normally open and the normally closed contacts, the real input contacts as well as some auxiliary contacts and some output coils. Now, what happens here is that let us look at this, that initially suppose the down solenoid is on. So, the down solenoid is on means this is on. So, this is on. When this is on, obviously, because you have an NC contact here, so therefore, up solenoid is off. So, the die platform is coming down. When it comes down, it eventually makes the down limit switch, and the down lamp will go on. So, this goes to 1. Immediately what will happen is that this previously the path that was being followed for connection was this. So, this down solenoid will become off. So, now at this position the down solenoid is off and the up solenoid is off. So, the piston is slowing down, there is no force forcing it down. So, it is slowing down. Now, what happens in this program is that the moment the down lamp is, so in this position the down lamp is on and the down solenoid has become off. So, now what happens here is that the down lamp is on. So, it becomes on, while the down solenoid is now also on. So, this is also on because the down solenoid is off. So, and this is a normally closed contact. Because this is a normally closed contact, so therefore, when the down solenoid is off, this is on. So, therefore, immediately the up solenoid becomes on. So, you see that normally for a die press the die has to come down on the, suppose it's a sheet metal on which you are trying to press into a particular form, then you do not want that the moment it comes below immediately it goes up. You want it to probably wait a little while and then go up for the next stamp. So, now it is a very it may be very common that a time delay between up solenoid and down solenoid is needed, that is after the down lamp is on and by the time the up solenoid again becomes energized, we want a delay. So, what I wanted to say here is that such delays are very often needed in industrial operations, and today we will see how to create these delays. Okay. So, we go on. So, now, so as we shall see, we will actually see the solution a little later, but first let us look at the timers which actually creates these delays. Now, here I want to mention that these timers, the timers are sometimes you have, we are all familiar with timers, we are possibly our first interaction with introduction to timers was in the digital electronics course. Now, those timers are actually hardware timers. You may actually use hardware timers also in a PLC, in which case you have a separate, you may have a separate timer card. But in this case we are talking of the program. So, it is actually a piece of code which creates a delay in asserting some output, right. So, the purpose of the timer is to create the delay. How much delay, that can be programmed, number one, and number two is that the timer actually, it's the basic idea of a timer is that there are two registers. One is called the preset register and the other is called the timing register. So, the preset register is actually set whenever you create a timer in the program, you actually set the preset register gets loaded by a particular value and it stays fixed. While the timing register, during the time that the timer is working, is active, the timing register keeps getting incremented using pulses from an internal clock of the PLC. So, it does not require any external clock. Sometimes you may also for example, as we shall see that counters are actually work on the external clock. So, because we want a particular timing, so generally it is fed from the internal clock. So, as the timing pulses from the clock are coming, so the timing register keeps increasing, and when its value exceeds that, every time there is a comparison between the timing register and the preset register. So, after some time what will happen is that the timing register value will exceed the preset register value, at which time the timer will stop timing further, that is the timing register will stop incrementing and the output will be asserted. So, the output will be asserted when TR equal to PR, right. Now, this thing happens when the timer is active. So, when is this timer active? That can be again controlled by using two kinds of logic. So, first is called the enable or reset logic. So, whenever this logic becomes 0, the timer is not enabled, it it's inactive and the output coil is reset to 1. So, this output coil reset to 1. When that is why it is called reset logic, reset to 0, I am sorry, reset to 0. Similarly, now when it is enabled, so at that time it is enabled to time, but whether it will actually time or not, that can be again controlled by this run logic. So, when this run logic will be enabled, at that time only the timing pulses come from the internal clock to the timing register, at other times it is inhibited. Okay. So, I would also like to assert mention that while in this case we have mentioned we have actually put it by a single contact, we could easily implement a complex logic based on which we want to enable or we want to assert the run logic. For that we can put extra rungs and which will actually program the logic, and then finally when the logic is satisfied or not, that will be simplified by that will be symbolized by an output coil. That output coil contact we can put it here. So, it is not necessary that you will have to always make it a very simple logic, you can make it as complex a logic as you want. So, having done that, so this is a basic timer. Now, timers create delay. So, we can have various types of delays and all of them can be realized by this basic timer module. So, to recapitulate, we have enable reset logic where the timing register is held at 0 when it is de-energized or 0 and the timer is enabled when 1. So, at that time the timer is ready to receive the clock pulses and increment its values. Similarly, we have run logic where timing register increments with the internal clock when the enabled reset logic is 1, that is the timer is enabled and the run logic is also 1, just what I said. So, now we take a look at the different kinds of timers. First is the on delay timer. So, here we are saying that if an input timer creates a delay between an input and an output. So, here we say that if the input signal goes on, then the output signal will go on after a little delay. That delay, that is why it is called an on delay. So, while the input signal becomes on, the output signal becomes on after a delay, and but if the input signal goes off, then the output signal goes off immediately. So, there is no delay in getting off, there is a delay in getting on, that is why it is called an on delay timer. Similarly, note here that here again it becomes on. So, here again it becomes on. Now, the timer, if this on would have persisted, then the timer would have been on somewhere over here, the timer would have been on. Because of this delay, but unfortunately the input became off, unfortunately or fortunately the input became off even before this delay interval could expire. So, the timer also became off and that delay value got erased. So, the timer never went on. Similarly, now we will see that we can easily realize this on delay timer using our old timer. So, now here is a circuit, here is a RLL logic circuit or a number of rungs which takes the basic timer unit, this is the basic timer unit that we have seen, takes it and couples it with another rung and makes an on delay timer. How? So, suppose we asserted this input and we want that. So, immediately when you asserted this output goes high So, immediately when we asserted this, this output goes high. But we want that the other output, that is OP002, actually go high after a short delay. So, what happens is that this whenever this OP001 goes on, so you see that the run logic is enabled and the enable reset logic is also enabled, which means that the timer is timing now. So, and when the delay so the timing register is getting incremented with the internal clock pulses, and when it will cross the preset register, at that time the OP002 signal will go up. So, you have this is wrong. So, you have created a delay. What is the on delay now? So, the on delay is this much. So, this is the on delay. On the other hand, see, the moment this becomes off. So, the moment this becomes off, immediately these two become off, and immediately the OP002 also becomes off. So, there is no delay in getting off, while there is some delay in getting on. That is why it is called an on delay timer. So, let us see the other kinds of timers. Now, before doing that, let us now, so we want an on delay, let us use this on delay timer now in our die press example to see whether we can introduce a delay between the that is after the down lamp goes on, we want that the up solenoid will go on after an on delay, right. So, we do that. So, here is our our earlier, the first two rungs are very similar to our earlier solution, except for this one. I am sorry. So, except for this one, right. So, now what is happening is that suppose the down solenoid is was on. So, actually the connection was coming like this. At this point, the down lamp suddenly became on, because the die hit the limit switch, down limit switch. So, the moment the down lamp becomes on, so this will off, and the down solenoid now goes down. Now, now look at this. So, initially the OP002 is off. So, therefore, this is off, and MCS, this is the master switch, this also becomes off. So, initially supply was coming up to this. Now, the down lamp has become on. So, immediately OP001 becomes on. When OP001 becomes on, the timer is enabled and it is timing. So, after a delay, this OP002 goes on, becomes on. When this becomes on, now there is a direct path to this, and up solenoid becomes on. And when up solenoid becomes on, so then that is then the usual operation starts. So, what we have demonstrated is that we have put a timer rung, and now there is a time delay which can be set by the value of the preset register that we set here between the down lamp coming on and the up solenoid coming on. So, that is what we have achieved. So, now we look at the other different types of timers, for example, off delay. So, the off delay timer is exactly like the on delay timer, except for the fact that now the delay is getting off. So, the moment the input becomes on, the output also becomes on, no delay. But when the input becomes off, the output becomes off after a certain delay. So, this is the delay, this is the delay. Okay. And the same phenomenon is actually observed, that if this becomes on again for a short pulse, see this also becomes on, then when it becomes off, here, this delay starts here, but before the delay, and then after this delay this becomes off. But in this case, before this this delay can expire, there is another on. So, it will again become on. So, this cannot fall because the delay has not expired. So, it continues, and then at the end of this again after delay it becomes off. So, basically the same, but just a very similar operation with the on delay, but only applicable in this case when the input goes from on to off. So, how do we realize this one? So, that is simple to realize. So, you see that now we are having off delay. So, again this is the input goes on. So, immediately OP001 goes on. When OP001 goes on, you see IN001, this is already off in the reset position. So, OP003 immediately goes on. This is my final output. So, there is no delay in getting on. Now, suppose, and when OP003 goes off, we can use this one. So, it latches. Now, imagine that IN001 goes off. So, when it goes off, this OP001, when this goes off, now these are NC contacts. So, when all the time when this was on, this OP002 was held to 0. Now, when it will be 0, then immediately the timer will start timing, and after some time this will become go high, become on. When this becomes on, immediately when this becomes on, this becomes off, and OP003 falls down. So, there is a delay in getting OP003 off. So, this is a very simple realization of the off delay timer, again using the basic timer construct that we have seen. Similarly, we could have various kinds of timers. For example, we could have a fixed pulse width timer, where every time the input becomes on, after there is a, irrespective of the delay, you will get a fixed pulse from the output. So, here this is just like an off delay timer. Yes, no, not an off delay timer. This is that every time when the input goes high, the output immediately goes high, and irrespective of the input, it stays for only for a fixed time and then comes down. So, here also when this goes high, and even if this comes down much earlier, this keeps. So, here it does not come down, but still this comes down, and here it comes down, but still this does not come down. So, every time you get the same pulse width. So, every time this edge comes, this ongoing edge at the input, you get a fixed pulse at the output. This is the fixed pulse width timer, and it will be an interesting exercise for you to see how this can be realized using our basic timer construct. So, that is a point to ponder for you. Next is that we again can classify timers into two ways. One is called retentive timer, another is called non-retentive timer. So, for a non-retentive timer, what happens is that see the input here goes up. So, the timing register starts increasing, suppose it is an on delay timer. After some time what happens is that the input comes down. Now, the question is at this point, so it has timed up to certain amount, it has not reached its preset value. So, now the question is that what will happen to the but the input has come down. So, what would happen to the timing register value at this point? So, in non-retentive timers the timing register value is reset to 0. So, every time you get another timing signal, it again times, and in this time because the input stays 1 for a much longer time. So, the preset value is reached, and when it is reached the timer output is asserted. See, here the timer output is not asserted because the timing register did not exceed the preset register value. So, this is called a non-retentive timer. Contrasted to this, there is a retentive timer, which now note the difference here. Here also when the input goes 1 and then after some time it comes down. So, the timing register value so the timing register value came up to this, it actually did not cross the preset register. So, the output is maintained to 0. Now, when this input falls down, at this time also the timing register value is not lost, but it is held. So, as long as the input is 0, it is held. For the next pulse, it counts from the previous value. So, that is why it retains its timing register value, that is why it is called a retentive timer. Finally, as this increases at some point for the maybe for the next pulse, it reaches the preset register value, and at that point the timer goes high. Okay. So, this is the semantics or meaning of the way the retentive timer works.